we've only looked at one type of potential energy, gravitational potential energy. And there are other types of potential energy, a big one being spring potential energy, which we'll address in a moment. However, I do want to talk about, in your book sort of jumps to this topic rather quickly, the idea of conservation of energy. And we talked a bit about that in the first lecture of this series for Unit 2.1. Basically, it states that the energy, which is again a measurement of the state of the object, is conserved. It can either be destroyed, or it can be transferred from one form to another. One easy way of transferring energy, one can see if you toss up a marker again, right? Energy is transferred from kinetic energy to gravitational potential energy, and then back to kinetic energy as it falls. So the initial kinetic energy of the object plus the initial potential energy of the object, again, the only potential energy we know about right now is gravitational, but it doesn't have to be just gravitational. The total energy, initial energy state of an object must be equal to its final energy state. In fact, at all times, the energy of the object remains the same, the total energy of the object. We are assuming here what are called conservative forces. And your book goes into more detail on what a conservative force is. But a conservative force is just a force where you can recover all of the energy. An example of a non-conservative force would be friction. Friction, you can't pull the energy back out once the energy goes into friction. Once the energy goes into heating an object up, you cannot easily extract that energy. Gravitational potential energy, it's easy to extract. Once kinetic energy of this rising marker goes into gravitational potential energy and stops, the force of gravity then takes that gravitational potential energy and turns it back into kinetic energy. Very little energy is lost in that transition with the exception of a little bit of drag force as this marker goes through the air. So friction forces and drag forces are non-conservative forces. They interfere with our concept of conservation of energy. Friction and drag forces actually take some of the energy of the system and put it into thermal energy of the object or the system it's in. And we'll talk about non-conservative forces in a bit. But if we assume friction doesn't exist, if we assume drag forces don't exist, then we can look at this relationship, rearranging the equations, putting the potential energy on the left, putting the kinetic energy on the right. We end up with the following relationship. Any change in potential energy, again, we only know right now gravitational potential energy, is met by an equal and opposite change in kinetic energy. Again, equal opposite does not mean vectors in this case. It just means that if there's a 10 joule increase in the potential energy, there's a negative 10 joule increase or a 10 joule decrease in the kinetic energy. So energy can be transferred from kinetic to potential or from potential to kinetic, but the total energy between the two always has to be the same. One way to think about it is think about a savings and a checking account in your bank. Your total balance might be $1,000. You have $500 in checking and $500 in savings. You can move $200 from savings to checking, or you can move $200 from checking to savings, but the total amount you have in your accounts is still the same. That represents conservation of energy. A common example of conservation of energy dealing with kinetic energy and gravitational potential energy is that of the simple roller coaster. So how does a roller coaster work? Well, dynamically, going back to kinematics and dynamics, right? There's a force of gravity downward that pulls this cart and accelerates the cart as the cart goes downward. The problem is the cart's velocity is constantly changing, right? So here the cart has, say, the initial velocity of the cart is 0, or initial speed of the cart is 0. But as the cart descends, the angle, using my marker to represent direction, the angle of the velocity changes, as does the direction of motion of the object as this object moves through that descending track. So the force of gravity in the direction of motion is constantly changing. This is a variable force problem. We cannot use our constant acceleration equations to solve this. You can solve it by using forces. You just need to know what the angles of the track are, integrate with calculus over this form, but it's a very difficult problem. A simpler problem is to look at the energies in the system. So, the initial track has some height h, right? 100 meters, 200 meters, whatever roller coaster you're riding. We're going to start off with all the energy and gravitational potential energy because the cart will be at its highest point. And the kinetic energy, as this right before you start to descend, the speed is very close to zero. So we're going to assume the kinetic energy is zero. So for the case of part A, right, the potential energy, gravitational, is maxed out, and the kinetic energy is approximately zero. Now, as that car descends, gravitational potential energy is being converted into kinetic energy. The car goes faster. That's the point of a roller coaster. When it reaches the bottom here, when the car reaches the bottom, it's at its lowest point. So its gravitation, since I define that to be zero, its gravitational potential energy at that time is zero. Its kinetic energy, therefore, is equal to the original gravitational potential energy, which is at some maximum value. So here, all the energy is in gravitational potential. None of it is in kinetic. Here, none of it is in gravitational potential energy. All of it is in kinetic energy. And then at some other point down the line, cart is here. Maybe at some point the potential energy of this cart is approximately equal to the kinetic energy of this cart. We can actually calculate at what height that occurs. So between these two heights, energy is constantly being transferred between kinetic energy and potential energy. The lower the height, the more energy is in kinetic energy. That's why the car goes fastest at the bottom of this ramp. And then that car's speed is converted back into gravitational potential energy when it goes over the next bump. You slow down to get over that bump, and then you speed up again. If there were no friction and no wind resistance, this cart could go over any hill that's equal to or lesser than the height of the original hill. That's why the original hill on a roller coaster, you're always at your highest point. As you slowly get cranked up to the top of the roller coaster. With friction, some of the energy is sapped, so you can never again get back up to that maximum point. And we'll talk about that in a moment. So if I know, we can actually put some numbers to this, right? Let's say the mass of the car, with everyone on it, is 500 kilograms. And the height is 100 meters. What is the initial gravitational potential energy of the cart? Well, we can calculate that, right? Potential energy gravitational is m times g times h. We know what the mass is. We know what the height is. G, I'm going to approximate it to be about 10, so I can do this math in my head. So you have gravitational mass will be 500 kilograms times approximately 10 meters per second squared. We all know it's 9.80, but I'm only going to worry about one significant digit, so I'm rounding it to 10. And 100 meter height. Gravitational potential energy is 500, goes to 5,000, 50,000, 500,000 joules. Because energy is in joules. So 500,000 joules initially, no kinetic energy. Well, what's the kinetic energy here at the bottom? Well, I know what it is. I know kinetic energy is 1/2 mv squared. I don't know how fast this cart is going at the bottom yet. But I know that the kinetic energy at the bottom of this hill has to be equal to the potential energy at the top. All of this potential energy goes into the kinetic energy at this lowest point. So at this lowest point, the kinetic energy is 500,000 joules. Potential energy is 0. Now, you might ask, well, how fast is the cart going? But I know that, right? 1/2 mv squared is equal to 500,000 joules. Well, we have to divide both sides by the mass of the cart, which is 500, multiply both sides by 2. Well, dividing this by 500 will give us 1,000. Multiplying by that 2 will give us 2,000. So the speed squared is equal to 2,000. It'll be meters squared over seconds squared. Sorry, I'm getting a little angled there. It's easier to write that way. 2,000 meters squared per second squared. So you have to take the square root of both sides, and I don't know what the square root of 2,000 is off the top of my head. Take the square root of both sides to figure out what the speed of the cart is at that point. Now the cart over here, let's say the height is halfway. Let's say the height is 50 meters. So h prime is, oops, use the same. Oh, it's green. Cart's green, so we'll use this. H prime is 50 meters. So the gravitational potential energy is 500 kilograms times 50 meters times about 10 meters per second squared. Again, I'm only using 10 as an approximation so I can do the math quickly. You'll want to use the actual 9.8 value in your homework problems. So here we have, well, it's half the height, so it should be half of it's 250,000. Gravitation is 250,000 joules at that point. You can look close to the edge of the screen there. Well, if 250,000 joules is in the gravitational potential energy, and the original energy was 500,000, where's the other 250,000 joules? It's in the kinetic energy. Kinetic energy also has to be 250,000 joules. So at each point, the total energy of the system is the same, 500,000 joules. If you add up the gravitational potential energy and the kinetic energy at the top, it's 500,000 joules plus 0 joules is 500,000 joules. If you add up the gravitational potential energy and kinetic energy at the bottom here, it's 500,000 joules. When you add up the gravitational potential energy and kinetic energy at the halfway point, half of it is in gravitational potential energy, half of it is in kinetic energy. And then with that kinetic energy, you can find out what the speed is at that height. Because I know what the total object is, in fact, the way I have this set up, the mass of the cart actually doesn't even matter. I could double the mass of the cart and the speed would still be the same at all points, assuming no friction, no air resistance. Because kinetic energy is 1/2 mv squared and gravitational potential energy is mgh. Both have mass in those terms. Those masses end up canceling. So it's a neat result that the object, its velocity at certain points doesn't depend on mass, which is actually what we learned about when we talked about the force of gravity. When you drop two objects of different masses, again, neglecting air resistance, they fall at the same rate.